to warn everybody. Okay, so it's my pleasure to introduce Alex Schenkel from Nottingham. He works on different topics in quantum field theory, higher structures, non-commutative geometry, and so on. To give a bit of history, he did his PhD in Würzburg, right, in non-commutative geometry and quantum field theory, and then had some postdocs in Germany, UK, and became a Royal Society fellowship holder in Nottingham at some point. So Alex, please go ahead.
Thanks a lot, Igor, and thanks for the invitation. Today I want to speak about boundary conditions and edge modes in gauge theory. And this is based on two previous works I've done together with my collaborators. In the first paper, I worked together with a bunch of people from Notre Dame University, Philippe Mathieu, Laura Murray, and Nick Tay. And the second paper is with my colleague Marco Benini and Benoit Vicedo. So the plan of my talk is as follows. In the first part, I want to tell you about how boundary conditions work in gauge theories in general, from a point of view using so-called stacks. I will remind you what stacks are. And if you take this stacky point of view, you will discover the so-called edge modes, which appear frequently in the physics literature. And I found that quite interesting, that taking this stacky perspective, the edge modes, which are kind of mysterious in the physics literature, pop up very naturally. So then I would like to illustrate this framework through a very simple example, namely Abelian Chern-Simons theory and Wess-Zumino-Witten theory on the boundary. And then I would like to discuss in the last part a bit of a more fancy example, namely the recent 4D holomorphic Chern-Simons and 2D integrable field theory correspondence, which was introduced by Costello, Yamazaki, and also in parts by Witten. Okay, let's get started. So first of all, I would like to discuss what are boundary conditions in ordinary field theories, where by ordinary, I mean field theories without gauge symmetries. So for concreteness, let's have a look at the scalar field, which I denote by phi. And the scalar field is supposed to live on a manifold M with non-empty boundary del M. So here's the picture. We have a manifold M and a non-empty boundary del M. So what is a boundary condition for such a field theory? So a boundary condition is simply a condition on the value of the field, or more generally on the jets of the field at the boundary. So for example, a boundary condition which everybody has seen before is the so-called Dirichlet boundary condition. When you take your scalar field and you restrict it to the boundary, you demand it to be zero. So the reason why people introduce boundary conditions is to have well-posed PDE problems. Okay, so the way of how boundary conditions are imposed can be illustrated, can be kind of made more clear by using a bit of a categorical point of view. Namely, enforcing a boundary condition, for example, that one, is a categorical construction which is called a pullback. A pullback is a universal construction in a category, and this happens here in a suitable category of spaces where we model our spaces of fields. So how does this work enforcing a boundary condition? So you have a bunch of spaces in the game. So you have the space of bulk fields, and you have a space of boundary fields, and you have a space in which you can compare bulk and boundary fields. And enforcing a boundary condition is then forming a pullback of these arrows. So let me show how that works for the Dirichlet boundary conditions. So we have a space of bulk fields, which are the scalar fields here. We have a space of boundary fields, which is just a point because I have a fixed field on the boundary, here given by the zero field. And I compare them by mapping the point to the functions on the boundary. This is where I do the comparison, and compare that against the restriction of the function in the bulk to the boundary. And if you compute this pullback, you get functions on M satisfying Dirichlet boundary condition. In case you want to have more fancy boundary conditions, like those involving derivatives of the field as well, you should put here some sections of a jet bundle. Okay. Now, what happens when we go beyond ordinary field theories? So when we go to gauge theories, where we have gauge symmetries, what happens is that things get more complicated because gauge theories require higher categorical spaces, which are called stacks. So let me give you a brief overview of what are stacks, and I just show you pictures and explain to you what they actually mean. So a stack is defined to be a pseudo-functor. So I work in the smooth context. So the functor starts at the opposite of the category of manifolds with smooth maps, and it goes to the two category of groupoids. And this pseudo-functor is assumed to satisfy a descent condition for open covers, which is two categorical in nature. So I don't want to explain too much about this descent condition, but I want to tell you how to interpret this functor. So a stack you should think of as a kind of smooth groupoid. Yeah, it's a groupoid with a smooth structure. But this smooth structure is kind of described in a more abstract way, namely through the functor of points perspective. So what this pseudo-functor here assigns to manifolds should be thought of as points of different shapes. So here I draw X. X is the stack I want to describe. And evaluating this pseudo-functor on the point R0, so the zero-dimensional Cartesian space, for example, I get the groupoid of points of X. So how I understand the evaluation of this functor on R0 is as the smooth maps from the point to the space I would like to describe. So evaluating this pseudo-functor on the line R1, I get the groupoid of smooth curves in X, and this is depicted here as well. So I want to describe the space X. And how do I describe it? By telling you how the lines smoothly map into the space X. And moving upwards in dimension, when you evaluate this functor on R2, then you get the groupoid of smooth planes in X, like depicted here, for example. So this kind of functor of points perspective is a bit different to what you usually do, which consists of using charts in order to describe smooth structures on spaces. Here you explore a space by telling how lower dimensional manifolds map into that space in a smooth way. And this is enough information to get things like tangent bundles, etc. Why is that so? Yeah, once you know what are the smooth curves in that space, you can say something about tangent. Okay, so let me give you an example to illustrate this a bit better. So a very simple example is given by gauge fields with a structure group G on, for simplicity, let's say a Cartesian space. U is a Cartesian space, Rm, m-dimensional Cartesian space. Then I tell you about the stacks of gauge fields of this type. I write it as con GU, so G connections on U. And this is a pseudo-functor, as defined here. I mean, a stack is a pseudo-functor, and I have to tell you what it does. What does it assign to a manifold N? To a manifold N, it assigns a groupoid, and this groupoid you have probably seen before. So the objects of this groupoid are certain one forms on U times N. So this 1, 0 means that the legs of the one forms are just on U. So it's just a function on N, but a one form on U. So this comes from the double grading you have on differential forms on product spaces. So this is, I tell you in a moment how to interpret that. But first, let's say, what are the morphisms? So the morphisms are given by G-valued functions on U times N, which do something you have for sure seen before. They implement gauge transformation. So from A, it goes to G minus 1 AG plus G minus 1 D. This is the de Rham differential. However, just the one on U. Yeah? G. So how this groupoid is interpreted, which I assign to a manifold N, is as the groupoid of smoothly parametrized by the manifold N, gauge fields and gauge transformations on the Cartesian space I'm considering. So in particular, if you want to know the global points of that stack, so you pick as N to the point, then you get a groupoid which you definitely have seen before, where the N goes away, and then you just have gauge fields on U and gauge transformations on U. Okay, so stacks when one hasn't worked with them, they sound horribly complicated, but when one gets used to them, it's not black magic. It's kind of a very natural structure. Okay. Are there any questions on this point, which I should illustrate? Okay, no. So yeah, please feel free to stop me at any point. So how does this stacky perspective change the way how one should interpret boundary conditions? So the key point is the following. So stacks, defined as pseudo-functors here. Oops, I deleted my stuff. Stacks form a two category. Why is that so? So between pseudo-functors, you have morphisms, namely pseudo-natural transformations. And between pseudo-natural transformations, you have another type of morphisms, namely modifications. So stacks form a two category where you have morphisms and two morphisms. And that means that when we want to implement boundary conditions through pullback constructions, we have to do that in the correct two categorical way. So because stacks form a two category, we have to use two categorical pullbacks in order to describe boundary conditions. And the way...
I think I missed when so you introduced the pseudo-functors.
Yeah.
Maybe you quickly said something about them, but I think I missed it. So they don't satisfy all the functor conditions, but they satisfy them only up to some...
Up to some yeah, isomorphisms. So for example, this pseudo-functor doesn't send compositions to compositions, but the pseudo-functor on the composition of maps is isomorphic to the pseudo-functor on the individual maps and then compose. So all the axioms which a functor satisfies, you can weaken up when you take functors with values in the two category.
Okay.
And the pseudo-functor. So everybody has seen examples of that. So for example, when you pull back vector bundles, and when you pull back along two maps, the result is different, but isomorphic to the pullback of the vector bundle along the composite map. So assigning the categories of vector bundles to manifolds behaves in this form.
Okay.
The pseudo here is not very important. I think the model I gave here is even strict. Yeah, pseudo becomes more important when you work on a space which is not Cartesian, where you would assign here the groupoids of bundles with connections, and then because you have bundles in the game, they pull back in a non-strict way, in a non-strictly functorial way. Okay. Yeah, but the key point is that between stacks you have maps, and between maps of stacks you have two morphisms. Yeah, so these things form a two category, which is different to the categories of spaces in ordinary field theories, which are ordinary categories. Okay, so so let me now illustrate how these two pullbacks work by giving you an explicit formula for this construction. So two pullbacks sound complicated, but they can be computed very explicitly in the category of stacks. So let's look again at this picture, which describes how one should think of as an implementation of a boundary condition. So here we have a stack. Now everybody here is a stack, and every arrow is a morphism of stacks. So we have a stack of bulk fields, we have a stack of boundary fields, and we have a stack in which we compare the two, in which we enforce our condition. Now, forming a two categorical pullback, I produce a new stack F, which you should think of as the stack of bulk fields, boundary fields together, enforcing this condition I want to implement. How these two pullbacks work is illustrated here, and I color coded that, so I hope that everybody sees color. I will tell you about the colors, so that in case somebody's colorblind doesn't suffer from this picture here. Okay, so bulk fields are denoted in black, boundary fields in blue, and the comparison data is denoted in red. So what are the objects in here? So forming a pullback, the objects are an object in here, so a bulk field, a boundary field, and an arrow in the comparison stack relating the restriction of the bulk field to the identification of the boundary field in the comparison data. So what does that mean is that instead of enforcing the condition, restriction of A is equal to IB, you have an arrow, so a morphism in this stack where the comparison happens between these two things. So, and this is probably something which you have heard before, namely the concept of equality becomes a bit different in a higher categorical context. Instead of saying A equal to B, you have to find a map, an isomorphism, witnessing that A is equal to B. And this is exactly what happens here. So you have bulk fields, boundary fields, and a transformation in the comparison stack, witnessing that restriction of A is equal to IB. And this is the key point, and this is why I denoted that by red. Now the morphisms between these kind of objects are as follows. So you have a morphism of bulk fields, phi, a morphism of boundary fields, psi, and they map from such a triple of data to another triple of data in the following way. So phi is a map from A to A prime, psi is a map from B to B prime, and they are compatible with these comparison transformations G. So restriction of phi, I psi, must be compatible with the G's. So the witnesses which enforce the boundary condition from this point of view, they are preserved in this sense under the morphisms. So let me give you
just maybe a comment. So if I understand correctly, the comparison that you're making is, the comparison in field theory language would be essentially a gauge transformation, right? So you compare two things, and then you say that they're the same up to a gauge transformation.
Yeah, if this comparison stack is a stack of gauge fields.
Right. Okay.
It can be also different. I mean, as we said before, when you want to encode conditions on derivatives of the field, then this can be a stack of some chats of gauge fields. So if here I try to be as general as possible. And down here I will give you a concrete example.
Okay.
And where it's really gauge fields. So the G is then really a gauge transformation on the boundary. Okay. Let me tell you about the example. And this is a quite nice example in my opinion. And I try to simplify it as much as possible by considering gauge fields just with structure group R to simplify as many things as I can. You can do the same example with a generic structure group. And if you want to see the details, you can ask me later about that. So I take gauge fields with structure group R on a manifold with boundary. And I want to enforce the following boundary condition, which I write here as a sentence. I want to say the following. I have a bulk gauge fields and they live on a bundle, on an R principal bundle. Okay, R principal bundles are super stupid. They are just trivial bundles or isomorphic to the trivial one, but still there's a bundle. Now I can take this bulk bundle underlying the gauge field and I restrict it to the boundary. And I want to set that equal to a fixed bundle on the boundary which I've chosen before. So these are gauge fields on a manifold with boundary, which such that the underlying bundle is trivialized on the boundary. So this is the boundary condition I want to enforce. And the concrete way how this pullback diagram looks like is now as follows. So we take the stack of connections on M, connections with structure group R, which I introduced on the previous page. So this describes the bulk fields. So bulk fields are connections, bundles and connections with structure group R on M. Now, as boundary fields, I just want to have a single one. Namely, I want to fix a boundary bundle. And the comparison happens in the stack of bundles on the boundary, del M. Now, the maps, what they do is this map here picks the fixed bundle I want to use for comparison. And this map here takes a bundle and a connection, forgets the connection, and restricts the bundle. And I can form the two pullback here. And if you use this explicit description I gave you up here for the two pullback of stacks, you see that the stack is as follows. So evaluated on a manifold n, so points of shape n in that stack are as follows. The objects are pairs consisting of a bulk field A, which is a gauge field, smoothly parameterized by n, by the test manifold. So here, the boundary field is just a point. I can drop that from the notation. And then the important part was this kind of morphism data. And this is now here, a gauge transformation in the stack of bundles. So gauge transformations of bundles are just group valued functions. And here for the real line as the group, it's just functions on del m times n for the reason that we smoothly parameterize. So, so let me say that again, because I kind of got a bit mixed up in saying that. Okay, so the objects consist of gauge fields in the bulk and gauge transformations on the boundary. And here this times n is just for the reason that I smoothly parameterize everything. So these gauge transformations on the boundary, this is exactly what people in the physics literature often study and give them the name edge modes. And the origin of the edge modes is exactly these two categorical pullback constructions. The morphisms between these kind of data are, so morphism is just a gauge transformation in the bulk, and it goes from A phi to A plus d epsilon, that is the usual way how connections transform, to phi plus the restriction of epsilon to the boundary. And yeah, so that is a nice and simple example, and you can consider more complicated examples. For example, when you look in the paper I wrote with Mathieu, Murray, and T, we also gave gravity as an example, because you can say I have a stack of metrics on a manifold, and I can restrict to the boundary and enforce a condition on the metric. Then you get also gravitational edge modes and other things. So you can, so this is a very general statement I'm doing. I just decided to tell you here about the simplest example. Okay. Now let me tell you about an application of this point of view. So Abelian Chern-Simons Wess-Zumino-Witten system. So in physics, this is known as the quantum Hall system, and it works as follows. So you have a three-dimensional manifold with a boundary, and you study Abelian Chern-Simons theory on this three manifold with boundary. And when you do that correctly, you see that on the boundary, you have degrees of freedom given by chiral currents. And this result can be nicely obtained from this higher categorical point of view I'm telling you about. And let me tell you now about the details. So let M be a three manifold with boundary, and consider gauge fields with, for simplicity, structure group R again, subject to the boundary condition we had before. Restriction of the bulk bundle is equal to a fixed boundary bundle I've chosen before. So on the previous slide, we have seen that the stack of such fields is of this form. So we have gauge fields in the bulk, gauge transformations, also called edge modes on the boundary, and they gauge transform as follows. And now, in order to set up the Chern-Simons Wess-Zumino-Witten system, what I need is a suitable action function on this stack F. Yeah. So I now enforced my boundary condition, and I now define you an action functional on this stack. So in order to define the relevant action function, I pick a metric, a Lorentzian metric on the boundary, because to say what are chiral currents, I need a metric. And I define an action function in the following way. In the bulk, I just take the usual Abelian Chern-Simons action, 1/2 A wedge dA. And on the boundary, I also add an action, and it is of this form. So it's now more complicated to read, so I have to slowly go through. So here I take this boundary degree of freedom, the edge mode, and I give it a derivative, and I wedge it with the restriction of A. So the reason I'm adding this term is because the Chern-Simons action is not gauge invariant on the boundary, when in presence of boundaries. So the gauge transformations of the Chern-Simons action produce boundary terms, and you need this term in order to produce a gauge invariant action. And then I add a new term, with a coupling constant lambda I'm commenting on in a moment, which looks like that. I use the Hodge operator corresponding to my choice of metric. And here I'm doing something which gets different names in different parts of the literature. So this dA phi is something like a covariant derivative of phi. But it looks careful, it looks different. It is not a linear map because it takes the differential of phi and subtracts a. It does not multiply with that. And the reason is that these phi's are gauge transformations and not kind of sections of associated bundles where you typically study covariant derivatives on. In other parts of the literature, these combinations are called dressed gauge fields, where I use a gauge field and a gauge transformation to dress it, to produce a gauge invariant quantity. And in fact, from this gauge transformation rule you see here, A goes to A plus D epsilon, phi goes to phi plus epsilon, you see that this particular combination is gauge invariant. So I can add this term as a boundary action, and the reason why I'm doing that is because when you now compute the equations of motion from this action, you see that this is exactly what you need in this Chern-Simons Wess-Zumino-Witten system. Namely, you have flat connections in the bulk, and on the boundary you have an equation which is of the form, this particular one form, dA phi plus 2 lambda Hodge star, dA phi is equal to 0. So now if you pick lambda plus minus 1/2, you see that this is exactly the chirality or anti-chirality condition for this one form, which is needed to have this chiral current on the boundary, which is observed in these quantum Hall systems. So, so I think, even though this example is not new, I think this perspective of enforcing boundary conditions through higher categorical techniques and then designing the relevant action for these stacks of fields is streamlining quite a bit of what is written in the physics literature. So I hope that you found that interesting.
Alex, so you're treating the action as a function on the stack, right?
Yeah, as a stack morphism.
Right. So as a stack morphism. So that means that it has to, I mean, it couldn't be just an arbitrary function of A and phi, right? It needs to satisfy some invariance condition.
Yes, exactly. So right.
So how is that verified for the formula that you wrote?
So the invariance condition is a gauge invariance condition, in fact, because I consider R as a group or as a stack with no morphisms, with just identity morphisms. So you must have a map which maps morphisms to morphisms. So gauge transformations must leave the value of the action invariant. This is the condition here. So how you verify that is you take this formula, you plug in this expression for the gauge transformation, and you see that the result doesn't depend on epsilon.
Okay, so the way that you see the invariance here is that you have to group the first bulk term, so the bulk term and the first boundary term together, right? Yes. So that is invariant, and then the remaining boundary term is also separately invariant.
Exactly, because these building blocks, these are something like, I find these dressed fields very similar to kinds of curvatures in an abelian, where you can build from the edge mode an invariant quantity in this way. And so these terms are individually invariant. And as you say, indeed, so when you have here a d epsilon, you have to use Stokes, you pick up a boundary term, and this boundary term is exactly compensated against that. Okay. So this term is not something I invented. This is well known in the literature. So people know very well which boundary term to add to make the action gauge invariant. I think this term I've never seen before written in a boundary action, written in an action. So I don't know if this is new or not, but it's exactly what you need to produce this chiral current.
Okay, and the chiral current. So the second equation enforced on the boundary. Are you thinking of this as an equation on phi on the edge mode, or as a boundary condition on the gauge field A, or both? I don't know.
I think there are different perspectives one can take. So when you vary such an action, there are three types of equation coming. I just dropped the third one because the third one is implied by these two in this particular example. So when you vary this action, you vary A, but the variation of A also is allowed to have support on the boundary.
Mm-hmm.
So when you vary that, you get three terms. You get the bulk part of the variation of A, giving you a bulk equation of motion, the boundary restriction of the variation of A, giving you one equation on the boundary, and the variation of phi, giving you another equation on the boundary. So this equation here is the one which comes from the boundary restriction of the A variation.
Mm-hmm. Okay, so I think in field theory terms, this would be like a natural boundary condition coming from the derivation principle. Like in the same way that I think Neumann boundary conditions are considered.
Exactly, yeah. So exactly, it's a good point. When you play a similar game with just a scalar field on the boundary, then this type of equation will be Neumann boundary condition.
Okay, and you said that you have another equation by varying phi. So what equation is that?
It's a type of Klein-Gordon-like equation, because when you vary phi, it's an inhomogeneous Klein-Gordon.
Yeah. Okay. So that would be like the Westermino-Witten type equation on phi.
Yeah.
Yeah.
Which is of course implied from flatness of A and.
Okay. All right. So I would say that the second equation you wrote is the boundary condition on A, or it's a common interpretation, and then the one that you didn't write would be like a dynamical equation for the edge mode.
Exactly. Yeah. And because of the very special form of this model, the dynamical equation is implied by chirality.
Mm-hmm.
Yeah, because chiralities automatically satisfy the Klein-Gordon.
But it's just interesting that you get to choose this lambda term proportional to lambda, because anyway. The connection between Chern-Simons and Witten I've seen before is where you take the gauge transformation of the action, and then it's the Lagrangian, you get an exact a total derivative, and then under the total derivative or exterior derivative you get something which you can use as a Lagrangian for the boundary on the gauge, acting on the gauge fields. But then that is kind of already chosen for you. It's not that you get to make a separate choice.
So I think when you just want to induce a boundary action from the violation of gauge invariance of the bulk action, then you will not see that term.
Okay.
So this I think just leads you to that term.
Right. Yes.
There's this paper by Pavel Mneev and others about where they study boundary conditions in this BV-BFV formalism, and they kind of give a construction of the boundary action.
Yeah.
In their framework, and they have to make other choices before, so they're again choices. But they produce a boundary action via construction, and what they get is not this term here. So I'm not sure how they get these chirality conditions.
But they also get something that they interpret in the same way.
I'm not 100% sure anymore. I read this paper long ago.
Okay, that's fine.
So they get something out, but they make other choices.
Okay, it's interesting how you do it. So okay, thanks.
So the way how we do it is rather non-standard, I would say. But for me, the order in which things have to happen is first impose boundary conditions, then define an action if necessary at boundary terms to model your physical system. So of course it can be argued. One can say, okay, yeah, let's first write down an action and then see how it is incompatible at the boundary, and then try to fix it afterwards via some previous choices I've made. So there are different points of view on that, but my point of view is first implement boundary conditions, then on the stack of fields satisfying boundary condition, define an action. And there you have, of course, the usual freedom. You can write down plenty of actions, and this simply defines different models. And And my statement here is simply that if you take this order I'm telling you here, then this action encodes this system. Okay. Thanks for the questions. Let me now go to something more fancy. Namely, I want to tell you now how these techniques can be used to get a better understanding of this 4-dimensional Chern-Simons 2-dimensional integrable field theory correspondence by Costello and friends. So I have to admit I don't know much about integrable field theory, so this might be very, very basic what I'm saying here. I don't know if you guys know about integrable field theory. So, but anyhow, to be on the same page, let me tell you what I know about integrable field theories. So I'm speaking about integrable field theories in 2 space-time dimensions. So these are integrable field theories on a 2-manifold sigma. And what are they? They are field theories where the equations of motion take a very specific form. Namely, equation of motion equals 0 can be written equivalently as a flatness condition on a certain connection. So L is a connection, I comment on that in a moment, and this is just the curvature of this connection on sigma. So L is a connection on sigma, which however is allowed to depend also meromorphically on some auxiliary space, on some auxiliary Riemann surface. So they call that a spectral plane or something like that in integrable field theory. So there's a spectral parameter in the game, which was denoted here by Z. So this I just learned recently when I started looking into integrable field theory. So for me, this was a bit new, and I had in mind always before people told me that integrable field theories have infinitely many conserved charges. And so the question was, how is this definition here related to conserved charges? And that's quite nice. And in case you haven't seen that before, I think this is the key point to understand the relevance of the Lux connection. So being able to write the equation of motion in this Lux form is super useful because you can use the Lux connection, study its holonomy, and derive infinitely many conserved charges from that. How do you do that? So sigma can be, say, a cylinder or a plane. Let's study the cylinder. I comment on the plane in a moment. And what we can do now is, so time I draw upwards. So when I pick now here as a surface, say a Cauchy surface at time t, and another Cauchy surface at time t prime, what I can do is I can study the holonomy of the Lux connection along that loop here, or along that loop here. And the nice thing is that the holonomy doesn't depend on which time I choose. Why is that so? Because the connection is flat. The connection is flat, so it doesn't depend if I use that curve or that curve, because the difference is the curvature integral over the region bounding these curves, and the curvature is 0. So this holonomy is independent of t. And now the infinitely many charges come from the fact that we have this spectral parameter. It depends meromorphically on that. So we can do a Laurent expansion. So when we expand in Z, we get from this condition that these holonomies don't depend on time, infinitely many conserved charges. And this is why Lux connections are useful. So when you play the same game on R2, so where the space coordinate is non-compact, then you have to be a bit more careful because then these integrations here generically don't exist. So you have to assume some fall-off conditions for the fields, of course. So the main problem in the integrable field theory community, as far as I understood it, is that they have a lot of techniques to produce models and Lux connections for models, but they all are a bit ad hoc, and there is a bit of the deeper understanding where the Lux connection comes from missing. And yeah, to appreciate that better, so here what I said above, that the equation of motion is equivalent to such a flatness condition, it's quite brutal to say that, isn't it? So the equation of motion is an equation in a set of fields, and then what you have to do is you have to invent a connection, expressing it in terms of the fields, which satisfies this condition, and also in a funny way depends on a parameter set. So this sounds like a very a non-straightforward problem to do that. But I think there was a lot of recent advances in understanding where these Lux connections come from, and this is due to the geometric approach via 4D holomorphic Chern-Simons theory, which Costello, Yamazaki, and in parts also Witten proposed. So what they propose is in a nutshell the following. So a geometric approach to construct two-dimensional integrable field theories on, say, R2 is to study a certain gauge theory on a 4-manifold X. X consists of the space, two-dimensional space-time sigma, and of C, where C is a Riemann surface. This blue part comes in a moment. So they want to construct two-dimensional field theories by starting in 4 dimensions, working on space-time times the Riemann surface, studying a gauge theory there, and extracting from this data a two-dimensional integrable field theory on sigma. And the input for their construction is the following. So you have to choose a Lie group G together with an inner product on its Lie algebra. You have to choose a meromorphic one form on, for simplicity, I just discussed CP1. So a meromorphic one form on CP1, so on this complex side, which has poles and which has zeros in general. So how you deal with those zeros is that the meromorphic one form is defined on CP1, and I remove the points where this meromorphic form is 0. So as the second factor of the 4-dimensional manifold, I consider CP1 minus the zeros of the form. The reason is that where the zeros of the form omega are located, this is later on where the Lux connection takes poles. So I have to remove those points. Otherwise Lux connections would not be part of the space of gauge fields I'm introducing in a moment. Then the key thing is what they propose is the following action, which should produce, after a two-dimensional reduction, integrable field theories. So the action depends on this omega, and it's defined on connections with values in G. So it's some prefactor integral over the 4-manifold omega wedge the Chern-Simons form, Chern-Simons 3 form. So this you easily see. The Chern-Simons 3 form is a 3 form. When I wedge it with omega, I have a 4 form. So this is a nice action on a 4-manifold. And then crucially, they implement boundary conditions for the gauge field on the points where the one form omega is singular. So Zi are the poles of omega, denoted here in red. And at these points, you have always space-time planes sitting, and they demand certain boundary conditions on these surface defects. Okay, so that is roughly their setup. And then they use this data and give some arguments how to produce a two-dimensional integrable field theory. I will streamline these arguments in a moment and tell you how this works from this edge mode perspective. But let me first say a few more words on the boundary conditions they're considering. So the way how these boundary conditions work drastically depends on the order of the pole. First, so simple poles, so first order poles of omega is where it goes easiest. So I will tell you about this case. And when you want to know about generic poles, then you can look at my paper with Benini and Benoit Vicedo. So crucially, what changes in the higher order pole case is that you also need jet information on the surface defect. So the surface defect becomes like infinitesimally thickened. This is essentially what changes. So the key point of why one introduces boundary conditions here and what is the role of boundary conditions is that this action I wrote down on the previous slide is not gauge invariant, which is something very similar to what happens in 3D Chern-Simons theory. When I have some boundary in 3D Chern-Simons theory, the action is not gauge invariant, so I have to do something. And here, the action is not gauge invariant because of the defect where the poles of omega are sitting. And so I have to do something. And the something which Costello and Yamazaki did is they proposed to enforce some boundary conditions to make the action gauge invariant. So the way how the action is not gauge invariant can be characterized explicitly. So if I look at the gauge transformation, here now we are in a non-abelian context, so I keep it. So this is the formula here. You see that the action on the transformed field is the action on the old field plus this extra term. This extra term here depends on the Maurer-Cartan form of the group and the Cartan-3 form of the group. And you pull these data back along the gauge transformation from the group to X. So this is the kind of violation of gauge invariance you see here. So the nice thing is that this violation of gauge invariance can be characterized very explicitly by using some homotopy theoretic techniques, like computing homotopy groups of mapping spaces, etc. And what you see is the theorem below here. And in order to explain that better, let me introduce a bit of terminology. So what is important in controlling this violation of the gauge invariance is what we call the defect group, which is the product over the poles of the group entering the system. So in the higher pole case, this would be a product over chat groups. And a specific inner product on the Lie algebra of the defect group. And this inner product here is related to omega. So the residues of omega enter as coefficients in this inner product. And then the statement is that expressed in terms of the defect group and this inner product, the violation of gauge invariance is of the following form. So the action on the gauge transformed A is the action on the old A plus an integral over sigma. So it localizes to sigma when you work out what that actually means. And what you integrate on sigma is the Maurer-Cartan form of the defect group pulled back along the restriction of G from X to the defect. And here you have the Cartan-3 form of the defect group, and you pull it back to sigma times an interval. And what you use to pull back is not G, because G is defined on sigma. G is any lazy homotopy between the defect value of G and the identity. And one can prove that these lazy homotopies exist in that case when you have a simply connected Lie group. So this is the assumption which I didn't specify here. So what you see is that the violation of gauge invariance of this action is something which is localized on sigma, which is localized on the defect itself. Okay, or in the near neighborhood. So that is similar to a Wess-Zumino-Witten term in an action. Okay, now the kind of boundary conditions Costello and friends proposed can be generalized a bit, and but they are of the following type. So the boundary conditions one needs in order to make the action gauge invariant. So we have to enforce boundary conditions to kill those terms here. And how can we do that is, of course, when we take A and G to take values in some suitable isotropic Lie subalgebra, then this inner product vanishes. So that guy vanishes, and one can also argue that that guy vanishes. So the idea is to impose boundary conditions by saying that the defect restriction of A is a one form on sigma with values in some isotropic sub-Lie algebra of the defect Lie algebra. And the defect restriction of G is a function with values in the Lie integration of this sub-Lie algebra. And if you impose these kind of boundary conditions, one can easily prove that enforcing them in a strict sense, I will tell you about the higher categorical point of view in a moment, enforcing these boundary conditions in a strict sense, as Costello and et al. Have done, defines a substack of the stack of gauge fields on which this action is gauge invariant. So we need these types of boundary conditions to obtain a gauge invariant action. So let me tell you about the higher categorical point of view on these boundary conditions. So we can enforce the same boundary conditions in a two-categorical way by forming a two-pullback. This defines another stack by a similar calculation as we've done before. And you see that there is a morphism from the strict boundary condition stack to the two-categorical boundary condition stack. Now, in this example, one can prove that this morphism is an equivalence of stacks. So in this model, in this four-dimensional Chern-Simons theory, you can work with both strict boundary conditions and two categorical boundary conditions in their equivalent perspectives. But still, the two categorical boundary conditions will be very useful in understanding where the integrable field theory comes from. And this is what I will tell you on the next and last slide. So where does the integrable field theory come from? And I think this is the main improvement of our paper compared to Costello and Yamazaki's paper, because using this weak concept of boundary condition, this two categorical concept of boundary condition, you see very clearly where the integrable field theory comes from. Okay, so here on the left, so the key is that we relate the stack of gauge fields with strict boundary condition, which was studied by Costello and Yamazaki, to a stack of two-dimensional fields. And we do that via a zigzag of maps. How does that work? Let me explain that roughly. So here, this is the stack where these boundary conditions are enforced strictly. As I've already said before, there is a map which is even further in equivalence to the stack where the boundary conditions are enforced in a two-categorical way. So in addition to gauge fields, you also have these edge modes as part of the data in that stack. But there's an equivalence between those. So this is just an equivalent perspective. Now in this bigger stack of gauge fields and edge modes, you find the substack of gauge fields, which are of Lux type. So connections which are of Lux type. So connections just having legs along sigma and having some suitable meromorphic dependence. So this step here requires solving half of the equations of motion, the bulk equation of motion of the system. Now, from this Lux type stack, you can project down to the edge modes only and arrive at the field theory on sigma. And this is the key point. So we have a zig, zag, zig. And we use this zigzag to transport the action, which was defined on here, to an action on here, which is a two-dimensional action for an integrable system. So how does this work? So transporting an action along an equivalence is no problem. So the action from here goes to here. It restricts along that map, that is fine. But here the arrow goes in the wrong direction. So you need further the datum of a section of this projection map on the boundary fields, on the edge modes. And this is a datum one has to choose. If I remember correctly, I think Benoit and a collaborator of his clarified the existence and uniqueness of such sections. And I think the result is that under some suitable extra hypothesis, such sections exist and are uniquely defined, exist and are unique. So having the action on here, we restrict it then down to here. And what that produces is quite nice. So writing the section as follows: S of H is L of HH, where H is a field on sigma with values in the defect group. So these are the edge modes in this model. You get a two-dimensional action from this construction, which looks as follows. So you have an integral over sigma of this term. So this is a bit inexplicit. So here you pull back the Maurer-Cartan form along H. Here you have the Lux connection. Okay, this depends on how you define a section. So the specifics of that model depend on the section you use or on the data which produces you the section. And here you have a term which comes from integrating over sigma times the interval, which is a kind of Westermino-Witten-like term. And these actions are by construction integrable systems, integrable field theories. Why? Because they come with the Lux matrix, which is encoded in that section, by the Lux connection, which is encoded in that section here. Okay. Last thing I wanted to say, okay, here this H hat is again a lazy homotopy from the edge mode to the identity, which again exists because of the topological features of this model. Okay, I think that is all I wanted to say, and I think it's also good in time. Thanks a lot for.
Thank you very much, Alex. So are there any questions? Please feel free to unmute yourself and ask. Okay, maybe I'll ask the first question. It seems to me that this 2D field theory that you're building, where the dynamical fields in the field theory are these edge modes, right? And the edge modes are dictated by the structure of the gauge transformations in this four-dimensional theory, which are group value functions. Am I right? So does that restrict the kind of integrable model that you can build, or is it just too naive a perspective?
So yeah, you're right that the edge modes are at the end functions with values in the defect group, and the defect group is either a product of the structure group of the bulk theory or of chat groups of the structure group. So you also get, but these are all sigma models, I think, what one gets here. These are sigma models where the target is in general the chat group.
Okay.
So yeah, the chat bundle on a group.
So like if you take Korteweg-de Vries equation, right? It's a well-known integrable equation, but it doesn't fit into this framework, right?
I don't know. Maybe I think Benoit is around here. I have to admit I don't know many examples. So I know that the usual West-Sumino-Witten model fits in here because Benoit once have shown me the Lux connection formula and how this works. But I was not involved in studying examples in this framework. And Benoit, are you still around?
Yeah, I'm here, but my child isn't next to me, so it's a bit noisy. But so yeah, you can only produce sigma models, as Alex said. So KDV is not an example that you can consider in this formalism.
Okay, thank you.
Yes, yeah. And sine Gordon is also difficult to produce. It's not really a sigma model. Yeah.
Yeah. So I'm, yeah, I don't know what is what is the perspective of Costello and Yamazaki on these things, because I think when you read their papers, which are unfortunately very long, but when you read a bit in them, you see statements like they hope to produce at some point a framework which gives all integrable field theories, but I think the current form is not yet of this type. So what you can get, so I think when you want to have a specific field theory, how you can control that is, yeah, so the choice of the meromorphic one form omega is the key point. Yeah, so you have to make there an appropriate choice, and the order of the poles tells you about how the target of the sigma model changes. Higher order poles give higher chats in the group, and so this is how you can design those things. And I think they gave classes of examples as well, how you can design the omega and the boundary conditions to build models which you would expect in there, but they're all sigma models.
Okay, any other questions?
So I have kind of very stupid question. Yeah, you say about the integrable system and the Lux representation, and of course that is a kind of zero flat connection. Yeah, so I think that's you can consider also finite dimensional integrable system, and you have also Lux representation, and then you have the same application to classical finite dimensional integrable system on finite dimensional in symplectic manifold.
Okay. Again, I don't know much about integrable systems, but I think the integrable finite dimensional ones also have Lux.
Yes.
Lux matrices, not Lux connections. So here the kind of thing is that you have a connection which is itself a field on space-time. So this has more components. So when you do some lower dimensional particle examples instead of field theoretic examples, I would expect that the sigma becomes just the timeline instead of a two-dimensional world sheet. And that probably leads to the concept of Lux matrix. And yeah, I think the flatness condition, as far as I understand it, is the key point also of this Lux matrix, Lux pair in finite dimensional systems where people produce many charges.
Yes, exactly. I mean, that's a, the people say that's a flatness zero curvature condition and the equivalent term, yeah.
Yeah, what I didn't see people doing before, maybe they did, I don't know. When I had a look at that, I was asking myself about three-dimensional integrable field theories, because this flatness condition has, of course, generalizations to higher dimensional worlds where you take, instead of a connection on a chirp. And the flat connection on a chirp would maybe be the analog of a Lux matrix in a three-dimensional integrable field theory, but I don't know if people studied that.
Yeah,
I can comment on this a bit. So there's some recent papers on some holomorphic six-dimensional Chern-Simons theory, where they can use it to extract anti-self-dual Yang-Mills theory, which is four-dimensional and is known to be some mother theory for many integrable field theories. So it's like a four-dimensional version of an integrable field theory, which contains in particular KP, which is three-dimensional.
Mm-hmm.
So I don't know how it's related to these Gerb connections, but it's integrable in some sense, and it's three-dimensional KP. And then anti-self-dual Yang-Mills is also four-dimensional and encodes information about integrable field theories. And then also this work by Costello and Yamazaki, it treats lattice models, which are finite dimensional systems. So, and the way they do it is by considering line defects rather than surface defects. So you have basically defects which are lines in sigma and points in CP1. And by doing this, they produce a lattice in sigma. And this lattice is sort of the lattice of the lattice field theory. And yeah, so I mean, their papers were explicitly about lattice models.
Mm-hmm.
So finite dimensional, yeah.
Good.
So I have another maybe quick question. So you mentioned that in one of your papers you studied the edge modes in gravity, which I presume would be some kind of a vector fields on the boundary of a space-time region, right?
Yes.
So what have you learned about them, and have people in GR noticed these things in some other language maybe?
I think we studied them not in detail. I mean, the referee was asking us to put one more example in the game to show that the framework is generally enough. So I wrote a short example on gravitational edge modes. Again, so I didn't learn anything in detail about them. Just that they what people like Friedel and friends are writing down can be produced from such a higher categorical perspective.
And what are they writing down? So
they are writing down. So they typically look at some Cartan, Einstein-Cartan gravity, where you have gauge symmetries and diffeomorphisms, and so then when you want to enforce boundary conditions, you get both the gauge theoretic edge modes, which are then functions with values in the Lorentz group, and you get gravitational edge modes, which are diffeomorphisms, or infinitesimally are vector fields, as you say, on the boundary, and then the space of gravitational field configurations under boundary conditions has then, of course, many building blocks. So you have a metric in the bulk, a vector field or a diffeomorphism on the boundary, maybe a Lorentz edge mode on the boundary, and so you can build plenty of actions. And these actions were studied to a certain extent by the perimeter people and associated people, and so at least the building blocks for these actions is what one gets from this higher categorical perspective. And I didn't study these actions in detail. Okay. Oh no, I studied these actions in detail. I gave it to a master student recently. But he computed a bit, and I think 3D Einstein-Cartan gravity, you can write down nice actions to have non-degenerate solutions, because when you don't write down a boundary term in the action, your field bind degenerates on the boundary, and so you can produce nice actions to have.
But what kind of dynamical edge mode equations do you get? Are they a wave equation like or something like that?
I think the point where the master student ended up with is to get those kind of mixing the matching terms correct, and the dynamical terms for the edge modes he didn't study it.
I see. Okay.
So yeah, in gravity it gets more nasty because you have so many things you can build up. Yeah, because you have as degrees of freedom a diffeomorphism on the boundary.
Mm-hmm.
You can essentially take whatever you like, pull it back along that diffeomorphism to produce a diffeomorphism invariant quantity. So you can write down whatever terms you like, and I don't know how to design reasonable models out of that.
It would be interesting if there was some connection with some BMS symmetry. Somehow, if the BMS symmetry could arise out of some dynamical equations on the edge modes. But that's just like first idea that comes to mind in terms of trying to.
So when you look into Friedel's papers, or Friedel and collaborators' papers, they studied a lot of speculative things about edge modes in recent years. So if there is a chance to have something like what you're looking for, I would expect that they already have discussed it.
Maybe I should have a look.
Certain level of a bit sloppy probably, but they will have discussed parts of that in their papers if something is around. So for example, they also wrote papers on how these edge modes are useful for electromagnetic duality and other kinds of things. So there's a lot of speculative and potentially interesting stuff out there.
Okay, very good. Any remaining questions? Right. If not, so let's thank Alex again.
Thanks.